Hello all. In this video we're going to look at how to run protein ligand docking through Rowan. So docking is one of these classic structure-based drug design techniques. You can read all about the fundamentals here on Wikipedia or in the primary literature, but basically the goal of docking is to predict, as it says here, the pose and orientation of a ligand, a small molecule, when bound to a protein receptor or enzyme. And it's really easy to do this through Rowan and very fast as well. So we'll just walk through that process from start to finish today. To get started with, we actually need a protein structure. So we can go over here to my project, sort of scroll down to the protein ligand section and select docking. And what we'll see here is we need to input our protein target. So either via PDB ID or via a PDB file or via these other sort of Rowan input methods here. You can select it from your project structures or from previous project history. For this tutorial, we're going to be using this crystal structure of ROC1 that's actually already bound to this pyridyl benzamide inhibitor from AbbVie. So you can see the paper here. They, identified this dual ROC1, ROC2 inhibitor. And as a part of this, they deposited this beautiful crystal structure here in the PDB. That's going to be our starting point. So all we need to do is just paste this 4-character code in. We'll say load, and then Rowan will automatically pull this in and we can visualize it right here. Okay, so a couple things might stand out to us here. So we've actually got 2 protein subunits here. We've got 2 ligands. This is kind of exciting. And we see this little, this little warning note saying that we probably need to sanitize this protein. So experimental proteins have all of these, experimental protein structures have all of these characteristics. They're often missing hydrogen. Sometimes there's solvent, cofactors, artifacts, salts, all these things that are done experimentally to actually get a clean crystal structure. But we need to remove all of these if we're going to go ahead and use this for docking. So we'll click Sanitize Protein. What we'll do is a few things. So first, we're just going to remove one of these chains. There's 2 proteins here. That's how it crystallized experimentally, but we don't actually need this. We'll remove chain B and say Apply. Great, so now we just have one. We can see that there is already a small molecule ligand in here. So this lovely ligand in green, which we can zoom in on here. That's fine, but that's not really what we want here. So what we're going to do is we're going to say save pocket for redock. And we have a choice here between which ligands we're going to save. So we can either save JOP, which if we go back here and scroll down, this is actually the name of the ligand of interest, or the other ligand here is sulfate. So that's just one of these salts that made it into the crystal. And we don't want to save the sulfate pocket because that's not actually a real ligand. So we'll say save pocket. Here we go. And then we'll say sanitize. Okay. So I've just fast forwarded through the wait. Sanitization here took about a minute. This is not uncommon. And if we look here now, there's all these unresolved residues that have sort of been added to the side here. So if we were going to run MD or some other calculations, we might worry about deleting these sort of unresolved tails that PDB Fixer doesn't know how to deal with. But for docking, it really doesn't matter, and we'll just leave them as is for now, just for simplicity. So now, if we're going to dock, we have our protein target all set up and configured, prepared properly for docking. And now we're going to need to input a ligand. And if we go back to look at this ligand, sort of to have an idea of what might bind, we can click on this 2D diagram here, and we can see that there's this pyridine, there's this sort of benzamide moiety here, and then there's this sort of, dangling off ring here with some catechol-looking functionality. And this is a fine ligand, but let's just try docking a simpler version of this. Maybe so we'll draw 2D. And we'll put a pyridine up here, then we'll put another benzene down here. So we'll make an analog of the ligand that works. We'll go back, so we'll have a benzamide here, but now we'll just put a propyl chain here. And so this is now we're sort of missing this bottom ring. Down here, we don't have this ring anymore. We just sort of have 2 carbons and then an extra carbon here, sort of as like a stripped down mimic, more like a fragment. And we'll save this. And then what we'll see is that we need to convert this into a 3D structure, and we'll do so here. And now we're all ready for docking. So we have our protein target. What we have here is actually we have the pocket defined. We could choose other ways to do this. So we could do a blind dock if we wanted to. We could manually specify a pocket, but in this case, we already know where the pocket is, so we'll just redock from the saved pose. And then we can choose our docking settings. So, we could go here and we could choose if we want to use autodock VINA. We could choose what scoring function. We could do quick VINA. We could choose the exhaustiveness or the number of poses. But for now, we'll just sort of leave it as default. And then we will keep pose refinement on so that we get cleaned up poses at the end. And we'll say submit. And there we go. And by default, this is just given the name of the smiles. But we can rename this and say example docking on rock 1. And it will say 6E9W, just to give it sort of the name of the PDB structure we started from. And if we want to add any more notes, we can go here and we can say, we're testing out Rowan's docking workflow on a PDB structure with a stripped down ligand. Save. And so that, we can save these notes for later, that if we come back to this next year and we don't remember what we were doing here, now we know. So the calculation is actually running. It's been running for 10 seconds. We have all this information saved here, all the settings that we submitted it with, and then some information about the compute hardware that this is running on and how many credits this is being charged. And we do now actually have this, all these log file details down here. We could go over here and we can see that docking has actually finished running already. So this is the pose with the lowest docking score. So we can focus on the pocket here and then sort of flip through. We can flip through the different poses and see the different ways that it tried to bind this ligand. Or we can sort of superimpose all of them and see that, yeah, there's actually a few different poses being explored here. So most of them are binding over here in this side of the pocket, but pose number 2 actually sampled a completely different arrangement of the ligand within the pocket, which is over here. And from this, we might actually be able to surmise that, if we add, if we take this propyl group over here and we sort of add more functionality over here, we might be able to make a longer ligand that actually fits the pocket better and is a much better inhibitor. That there's actually space to sort of connect the blue and the red fragments and make one longer ligand. And if you remember, right over here, sort of in this, this propyl group right here was where we actually had the other rings coming off here. So if we didn't already know that we could accommodate additional functionality over here, we maybe could learn this from this docking calculation. Obviously, in this view, you can see all sorts of other things. So we can look at the individual interactions. There's this backbone amide that's hydrogen bonding to the pyridine and all sorts of other things going on. Maybe some pi interactions going on with this system and some methionine side chains. We could always do energy decomposition analysis to try to pin that down if we wanted to in more detail. And then, of course, we can submit this, to molecular dynamics. We could use this as the input to FEP. We could do all sorts of things with this. But yeah, in a nutshell, this is how docking works in Rowan. And the last thing I just want to emphasize is that docking is really, really fast. So this just took 30 seconds here, including, actually building the receptor, optimizing all the output poses, saving it, all of this stuff. This is, very, very quick. And if you do sort of batch docking for organization customers, that actually gets down to, a second per compound or even less. So there's a lot of ways to sort of predict protein ligand binding. Docking is by no means the most accurate, but it is among the fastest, and that makes it very useful.